Section 5.3 Least Square Problems. This section is about the least square method. The least square method is a popular method in numerical analysis and statistics. It's used to find the least square fit to a set of data points in Rn. This method was developed by Gauss. Let's consider the system Ax equals b. In this case, A is a m by m matrix, and b is a vector in Rm. For this system, we know there are two possibilities. The first possibility is the system is consistent. That means there exists a solution X for these equations. A necessary and sufficient condition for Ax equals b is consistent is b belongs to the vector space Ra. The second case is, or the second possibility is, the system is inconsistent. That means no x satisfy the equations Ax equals b. For that, a necessary and sufficient condition is b doesn't belong to Ra. Now what are left is we need to think about the second possibility. So here is the question. Given an m by m matrix A and the vector b belongs to Rm, if b doesn't belong to Ra, in other words, the system Ax equals b is inconsistent. The question is it possible to find a vector x belongs to Rn, and the distance between b and a times x is the smallest. This question here is the same as the next question, in the sense of when we take a look at the square of the function above. Because find the minimum value for this distance is the same as to find the minimum value for the square. I'm sorry, how to get rid of this part? Okay, there. Why we take a square of the distance? Because it's relatively easier to deal with the square rather than the distance. If we take a look at this form, then we can get the idea why it's called the least square problem. So here you can say we have this distance square, so that's the square. Least is because we want to have this distance square is the smallest. So in that way, get the least. So that's why we call this is the least square problem. Let's take a look at the theorem 5.3.1. This is quite a general result. We assume S is a subspace of Rm, and B, the vector, belongs to Rm. So the last part, or the last assumption here is the same as what we talked about in the least square problem earlier. The first conclusion is there is a unique vector P. P belongs to S. That is closest to the B. What's the meaning for the closest? The closest means the distance between B and Y is greater than distance between B and P. For any vector Y belongs to the subspace S, but Y is not the same as P. So that's the meaning for the closest by distance. The second conclusion is this. Suppose P is a vector belongs to the subspace S. Then P is closest to the B if and only if B minus P belongs to the orthogonal complement of S. Let's start the proof for the first part. First of all, we need to use the theorem 5.2.3 we studied in the last section. Based on theorem, we know Rm is a direct summation of S and its orthogonal complement. So Rm equals So plus the orthogonal complement of S. Then we consider a vector B. Recall we have B belongs to Rm by the assumption. Based on the theorem, the B can be numerically written as the sum of P and Z. Here, P belongs to the subspace S and Z belongs to the orthogonal complement of S. Now, for arbitrary Y belongs to the subspace S, we calculate the square of the distance between B and Y. Now for this, we substitute B by this representation, B equal to P plus Z. So we got this form. Then we regroup for these three terms. We write this as P minus Y and then plus Z. Because P belongs to S, Y belongs to S, then P minus Y also belongs to S because S is a subspace. And Z belongs to the orthogonal complement of S. For this, we can calculate this square of the summation. We know this square of the distance is the same as the first term, take the distance and then square it. The second term for Z we look at is square. And then we should have the third term, that's the double of the scalar product of P minus Y and Z. But P minus Y belongs to S, Z belongs to the orthogonal complement of S, so that these two terms or two vectors are orthogonal to each other. So in this way, we got the square of the distance between P and Y, and then plus the square of the norm of Z. Now for this, we substitute Z by B minus P. This is gathered from the representation. We have B equal to P plus Z. So both sides minus P, then we get B minus P equals Z. So we do this substitution. Now we can say we have two terms here. The two terms here both get squared. So that means these two terms are at least 0. So when we drop the first term, we should get this is greater than or equal to the second term. And then we want to know in what kind of case or condition the square of the distance between y and b is equal to the square of distance between b and p. Now for that, we should have this term equal to 0, right? So for this term equal to 0, that means the distance between p and y equal to 0. That equals 0 means y equals p. So in this way, we get the first conclusion in the theorem. So for any y belongs to S, we have the square of the distance between y and b is at least equal to the square of the distance between b and p. To reach the strict inequality, we need y not equal to p. If y equal to p, then we can say, of course, these two parts are the same. Now let's consider the second part of the theorem. If P belongs to S and B minus P belongs to the orthogonal complement of S, then we can write B as the summation of P plus B minus P. Now this you can simply say P and negative P cancelled, so that's got the right side equal to the left side. But P belongs to S, B minus P belongs to the orthogonal component of S. So in this way, you can say this is a direct decomposition for the vector B. And then from the first part, we can say P is closer to the B. Why? Because if you take a look, this kind of form, you can say B equal to P, just like what we had earlier, and then plus Z. Now, precisely the Z is B minus P. Why? Because B minus P belongs to the orthogonal complement of S. Why Z equal to B minus P is because that decomposition is null, so that we get this is true, and in this way we say P is closest to the B. Now the other possibility, if we have a vector q. Q belongs to S, but B minus Q doesn't belong to the orthogonal complement of S. Then, in this case, we choose y equal to q in the first part. Then we can say this square of distance between b and q should be greater than the square of the distance between b and p. So in this way, we showed the second part. The second part is a necessary and sufficient condition. What we're going to do next is we're going to apply this theorem to the least square problem. How? In this case, what we're going to do is we're going to choose the subspace S equals Ra. And then from theorem 5.3.1, we got a solution for the least square problem. So consider the matrix A and the vector B. We now have 4 statements. These 4 statements are equivalent. The first statement says the square of the distance between b and x is minimized. The second statement says b minus ax belongs to the orthogonal complement of Ra. The third statement says b minus ax belongs to the null space of A transpose. The fourth statement is a equation. The transpose of A times x equals the transpose of A times B. Now, let's take a look how to prove these 4 statements are equivalent. First of all, let's look at why the first statement and the second statement are equivalent. To do this, in theorem 5.3.1, we just proved take S equal to Ra, then consider x. X is a vector belonging to Rn. Then we multiply the x by A. Then in this case, we can say Ax belongs to the vector space Ra. And then by the theorem 5.3.1, the second part, we can say Ax is close to the B if and only if B minus Ax belongs to the complement of Ra. Now, in the theorem, the second part, we actually pick up Q equal to Ax. So the condition in the theorem is B minus Q belongs to the orthogonal complement of S. Now S equal to R. So that's why statements 1 and 2 are equivalent. Then for the second statement and third statement, their equivalent is because this ratio, the orthogonal complement of Ra equal to the north base of the transpose of A. That's the result we know in the last section. For the equivalence between the third statement and the fourth statement, we can say B minus AX belongs to the north space of the transpose of A. That means if we take the product of the transpose of A and B minus AX, that should be 0. So take a look at the definition for the north space of AT. Then we can say that's necessary and sufficient. Now for this, we can say that is the same as the transpose of A times B minus the transpose of A times X equals 0. So from this we get this equation. There is a particular name for these equations. Is called the normal equations. The normal equations means we have for the transpose of A times X equals the transpose of A times B. So here we have for equations. Now for these equations, we can say how many equations we have. Well, for this, we can say A is a m by n, so its transpose is m by m. M by m times B is m by 1, so this is m by 1. That means here the normal equations actually contains n equations. Now we give a direct deviation for the results we got there. Here is the statement. We consider M by M matrix A and vector B. B belongs to Rm. If X hat is a vector belongs to Rn, this vector satisfies the normal equations, then the conclusion is the distance between B and A times the hat X is the smallest among all the distance between B and X. Here, X is a vector in Rn. Now we are going to give a proof for this statement. To do this, what we're going to do is actually we take a square for this equation here. So we want to show the square of the distance between B and X is greater than or equal to the square of distance between B and A times the hat X for any X belongs to Rn. If we can show this, that means the left side is reach the minimum value for the left side. Based on the assumption x belongs to R, the head of x belongs to Rn, and this vector satisfies the normal equation. So we got A transpose times B minus A x hat equals 0. So this is just we move the right side to the left and then pick up the transpose A, then we get this. And for this, both sides we take the transpose, then we get the second equation. Then we take a look at the square of distance between B and AX. Now this square of distance is the same as the scalar product of the vector and itself. For this, we do a simple algebra. We take away a x hat, and then to keep the value, we add this up. So we add, oh, I'm sorry, this should be minus. This should be minus. So b minus a x hat, then minus brackets ax minus ax hat. The same for the second term. I will change this in the latest, the PDF file. And then here, this is the scalar product. We can take the transpose for each of these two terms. So we get the first term, take the transpose, the second term, take the transpose, but here this should be minus. And the same thing for the second part here, this should be minus. Then we can say we have here two terms for the first brackets, big brackets. For the second term here we have two terms. Then we do the multiplication. So that is the first term times the first term, we get this. First term times the second term, we get this. This should be a minus sign. And the same thing here, the second term times the first times. This should be minus. Recall here should have minus. And then the last two terms to the product. So then for the second term here, you say we have ax and ax hat. So they shared a, so we moved a out. When we move the a out, then we can say this red part. Take a look at this red part. The red part is the same as what we observed earlier. That's 0. So 0 times x minus x hat. So this term should be 0. So actually it doesn't matter. Even here, the symbol is negative sign. And then for the third term here, the third term here is a times the bracket x minus x hat transpose. Now for that, we can say that's actually due to transpose. Then we should get the x minus x hat transpose first, and then times the a transpose. But look at the transpose of A times B minus AX. That's the term we say earlier. That equals 0. So this third term equals 0, although this symbol is negative. So in this way, we got the first term. Actually, this is B minus A hat X, and is self scalar product. That's, we know that's equal to the square of the distance of B minus AX hat. Similarly, for the last term there, that's the square of distance between AX minus AX hat. Now we got two square terms. Two square terms, at least the value is 0. If we drop the second part, we should get this is greater than or equal to the square of distance between B and AX hat. So in this way, we got the square of B minus AX, the distance there is greater than or equal to the square of the distance between B and AX hat. And in this way, we got a direct deviation for the least square problem. Now from this we can say for the least square problem, the solution is given by the normal equations. So the next we'll concentrate on how to solve the normal equations. So what we need to do for the least square problem is actually to find the solutions for the normal equations. So that's our next question. Theorem 5.3.2. Suppose A is an m by n matrix of rank n. Then the normal equations A transpose times A times X equal to B has a unique solution. The solution we denote by X hat. X hat equal to the inverse of A transpose times A, then times B. In this case, the X hat is the unique least square solution of the system AX by B. Here is the proof for the theorem. By the assumption A is of rank n, then the transpose of A times A is non-singular. It's non-singular, then for this system A transpose times A times X equal to B, we can find a unique solution. Simply, we just multiply these equations from the left side by the inverse of this part. Then we get the inverse of A transpose times A times A transpose times A, that's equal to identity matrix. So the left side we get X, and then the right side we get That's the product of inverse of A transpose times A, then times B. So we got solution. Now this solution, of course, is uniform. So for the normal equations, we can have a unique solution if the matrix A transpose A is non-singular. Then we need to consider the opposite. The opposite is if we got a case is the transpose of A times A is singular. Then the first question is there a least square solution to the system Ax equals b? The answer for this is yes. That's actually we say earlier. We can have a least square solution. The second question is how many solutions there? Now this is different from the case in theorem 5.3.2. In the singular case, we got infinite many solutions for the least square solution to the system X. Then the question is how to find a solution among infinitely many solutions. Now to do that, all we need to do is we need to try to solve the normal equations. A transpose times A times X equals B. So that's all needed to do. Now from this we can say there are two cases, but no matter which case, for the two cases we need, the first case is the transpose of A times A is non-singular. In that kind of case, the normal equation has a unique solution. The second case is A transpose times A is singular. In the second case, we need to solve the normal equations. There are infinitely many solutions. The question is we need to solve these equations. We need to solve these infinitely many equations. Now how to do that? Here, let's take a look at an example. Now in this example, we have matrix A. Matrix A, we can say this is a matrix. It has 3 rows and 2 columns. So this is 3 by 2 matrix. And the vector B is a 3-row 1 column. Now in this case, we consider the system Ax equal to B. We want to find the least square solutions for this system. To work on this, we need 3 steps. Step 1, we need to find the product A transpose times A. Sorry, this is not A transpose times T. This is A transpose times A. And say whether or not this product is singular. Now we can easily calculate A transpose times A. So this is A transpose, this is A. Now this product, we got this. And if we look at this matrix, this is 2 by 2 matrix, is a square matrix. For this matrix, we can say the first row and the second row actually there is a relationship. If we multiply the first row by 2, then we get the second row. So from this, we can easily say this matrix here is singular. Or you can calculate its determinant. Determinant is 0. The second step is to evaluate A transpose times B. Now that gave us this form, this vector. This is 2 by 1. The third step is solve the normal equations, Ax equals B. So this is A transpose times A, then times this is X, equal to A transpose times B. Now for this equation, we can say, here we can say we have 2 equations. But if we look at the second equation actually is the same as the first equation times 2. So that means we just need to solve the first equation. Let's look at 6 times x1 plus 12 times x2 equal to x. For that, we can let x1 equals alpha. Then from there we can find x2 will be equal to 1 minus alpha divided by 2. So in this way, we can say there are infinitely many solutions for the normal equations. And these solutions are of this form. The form is this. This is a vector with 2 components, alpha and 1 minus alpha divided by 2. Because alpha is arbitrary real number, so that we can say we have infinitely many vectors like this. And all these are the solution for the normal equations Ax equal to B. So that's the solution. All right, that's what.